All right, I think we'll go ahead and get started. It's a pleasure to welcome you again to this breakthrough series. And today we have the delight of welcoming Kevin Bishop from Uppsala University in Sweden. Before we get started, I want to thank Howard Weeder, as always, and the Canada Excellence Research Chair for funding this series. And to remind you that next week is Kamini Singha. Kamini is an associate professor at Colorado School of Mines, and she'll be talking about breakthroughs in the application of hydrogeophysics to water resource problems. But today we have Kevin Bishop with us. Kevin started at Haverford College, I think with a degree in philosophy, went to the UK, actually did a master's with Howard Weeder in engineering at Imperial College London, I guess the engineering hydrology program, and then went on to do a PhD at Cambridge. He worked with Dick Chorley, a luminary in our field. You might have been Dick's last student, I don't know.
No, there was one other.
One other, but really went on to produce what is, I think, one of the best PhDs that we've had in our field, focused on acid deposition and how catchments store and release water in relation to their chemistry in Sweden. Since then, the uptake of this work has been enormous. Kevin has worked in many places throughout Scandinavia, has been involved heavily with journals. He's been an associate editor for the AGU journal Biogeosciences, has been an associate editor for Hess, and has really been a thought leader in terms of how to link flow pathways, flow processes with biogeochemical transformations. Some of his new work is focusing on mercury and mercury transport, and you'll hear, I think, today a whole host of things relating to biogeochemistry of Nordic catchments. So again, it's a great pleasure to have you here, Kevin.
Thank you very much. Oh, wow. Thank you very much for that very generous introduction. And I hope, Howard, you'll be pleased, because everything I learned about hydrology came from that year in Imperial. Having been working in Scandinavia for the last quarter century, the title is breakthroughs. I mean, we don't do breakthroughs in Scandinavia. We do incremental change. We're very modest in that country. So it's quite a challenge for me to think, okay, I'm going to talk about breakthroughs. And I want to relate this to a sandbox, which is how I basically see Scandinavian hydrology. A great big sandbox, very simple. And I think it's thanks to that simplicity in the hydrology, we can offer something to the world in the way of a few things that, well, breakthroughs, I don't know. The breakthroughs I'd like to talk about or allude to are going to have to do with greenhouse gases, mercury and acidification, some of the problems we've been wrestling with in Sweden over the last decades, but also the natural background. I mean, when you ever go look for human influence, you've also got to think out what is going on naturally. And we have a natural range in the organic carbon of our surface waters that is a huge impact on the pH, on what lives in the water, on the metals, the toxins, and this is sort of within a few square kilometers, you can find all of this color in water. And if you want to stick around for a while and wait for a flow event to come by, any one water will move up and down this range of colors we have, because carbon is so dynamic in space and in time at different time scales. So we have to understand the chemical pollutants we're interested in. We've also had to understand this natural system. Now, those are the chemical things we're trying to do. And what is our secret weapon? What is the relation to hydrology? Our secret weapon is this landscape of Fennoscandia, which was bulldozed by the glaciers 10,000 years ago, nicely mixed up, leave a nice, relatively even layer of tills. And if you look at these colors here, the more intense red, the more of the landscape is covered by tills. And it's just wonderful, because this idea of your boundary conditions, what's underneath your catchment. In these till catchments, just more and more till, more and more compact, no cracks, no fractured bedrock to complicate life. It's a nice bottom condition and a reasonably homogeneous medium to work with. It's what I would call our sandbox, which should make the hydrology very simple. And in fact, if you want to be a hydrologist, do not go to Sweden, because they have plenty of water, they have very simple hydrology, and they're very good hydrologists. So why would you be there? That is why I've had to work with the nasty pollutants the society has given us. And the story I would like to tell today is going to be sort of a stereo. We're going to talk about some stream biogeochemistry, but there's also the shallow till hydrology. Now, remember how exciting it was if you got one of these things as a kid, at least when I was 8. Think of stereo as something interesting, but 2 messages is a little bit difficult, but that's what I'm going to try to do today. The first message about some of these pollutants, nitrogen, phosphorus, mercury, carbon, the organic pollutants, they all have chemistry of varying complexity. And to deal with this chemistry, it's not enough to take the unit hydrograph or some very simple representation of hydrology. We want something that is more like particle tracking. This is, to me, the ultimate picture of Hillslope hydrology. It is something that Keith Beven and his colleague Jessica Davies have been developing since Keith came up with the idea in the late 80s, but it's only been Jessica who started implementing this to see where each particle of water goes explicitly over time. Not just how long it spends in the catchment, but the pathways it takes that moves through the catchment, because those pathways have different geochemical conditions that will lead on to what eventually ends up in our stream and in our soils. And this is not just a matter of transporting pollutants, but it's also very critical, we're discovering, to the global carbon cycle. Some colleagues who are limnologists put up this picture of the leaky pipe. They point out that what comes from the land in the way of picograms of, or whatever, huge numbers of carbon coming out of the landscape, not all of it makes it to the sea. They focused a lot about what goes up to the atmosphere. It's here, there's 2 picograms of carbon per year coming out of the landscape, being transported to the seas in water. And when you compare that to the total global carbon sink, they're in the same order. You know, what's coming into the terrestrial landscape, almost as much as being sequestered, is going out in the waters as organic carbon. What we have discovered more recently is that in addition to the organic carbon that breaks down, there's all sorts of CO2 that organic carbon breaks down. A lot of it breaks down in lakes, but some of this is breaking down already in the soil and coming out at 10 times the atmospheric pressure, 20 times the atmospheric pressure of carbon dioxide into our streams. But it's not been recognized because it evades within an hour or 2. So when you're downstream measuring the CO2, you see a bit of CO2 going down, but you've missed all the CO2 that's gone up from your stream already. And this essentially doubles the aquatic conduit, at least in the boreal zone where we've been working in Sweden, which I think is big news. If it really is that case, we've got to think again about the terrestrial carbon sink and the role of water in getting it off the landscape. So these are some of the things that I'd like hydrology to help us with. And this comes to the hydrological side of our talk. We, as hydrologists, would like to help society figure out flooding, irrigation schemes, drought, and we've been able to do that tremendously successfully for a century with some very simple concepts. Again, back to our unit hydrograph, which we love to teach students about. Overland flow. It's all simple and you can see it. And I like to see this as, Mickey Mouse here, as we're Mickey hydrologists here. We want to help the world, and we're going to model where the water goes, tell it where to go. And it's really worked very well. Things like the Hoover Dam here being built. We didn't have transit time distributions or flow pathways. Very simple representations could help us do great engineering feats. But as we all know, if we studied Mickey Mouse and A Sorcerer's Apprentice, things can go badly wrong if you don't get it right. If you do things, you get the right answer for the wrong reason. It may work with a hydropower dam, but if you're trying to understand geochemistry, it's going to lead to some very misleading results. And this, I would say, is the dilemma that us hydrologists have. Simple explanations have worked so very well. If we sort of take water, if I take this water that's in here and I pour it on the floor, and you could work out very explicitly where each molecule of water is going to go and how long it will take it to go there. But if I take this water and I pour it into this little flower plot, I could give you a Cray computer and you couldn't tell me the fate of that water, how much will go down, how fast, how much will go back up. You could give it in rough numbers, sure, but explicitly, particle for particle, like you could do if I poured it on the floor, it doesn't work. Now, why is it that we are so confounded by this simple system? Well, to do that, I think we need to look into this. Excuse me for a minute here. It's really frustrating as a hydrologist to have to deal with this. I mean, to begin with, look at, there is, sorry about that I thought I'd keep it all off the floor, but I got some on the floor. But these particles, they have different sizes. They have a different configuration as you go deeper. It's not a homogeneous medium. You need some sort of a tensor description of the hydraulic conductivity. If we push this way, water will go in different directions. And then if we dig deeper, there are these, I think there should, look at these roots. I mean, it's easy to say that water follows very simple rules. It goes from high energy to low energy. It's like a couch potato, wants to find the lowest energy. So it should just move downhill. And I can easily say that to my students. In Sweden, for half of the water that falls as rain goes downhill to the stream. But the other half, it goes back up through these roots into the transpiration. That complicates life. And these roots, they create pores, macropores. Oh my gosh, we've got to talk about two-phase flow systems. That'll really set your computer going. And then when these roots have been around for a few months, they die. And what do they do when they die? They come back to haunt us as zombies, as organic matter that further changes the hydraulic properties of the system and will be hanging around for centuries or maybe a few months. We don't know. The carbon cycle in soils, you just get a little system like that and it's suddenly so complicated. And yet we were able to do big engineering hydrology without worrying about any of this. But if we want to start getting into the real geochemical questions, we can't ignore the complexity of the soils. And that is where hydrology is sort of, where I have retreated to the sandbox. Here's a representation Marcus Weiler did of a simple flower pot situation. You pour in the water, you can see how the water disperses, and that's just where its first few hours, and then it's going to spend weeks to months in that system, and how it comes out, anybody knows. And this is where we have a bit of an identity crisis, I'd see, in hydrology, is there are the engineers, people like me that would like to get the right answer or get an answer and get on with it and do something else. But they're the scientists who want to really understand this. And I don't know, what is hydrology? Are we a science? Do we really have to have some guiding principles, or just have to get a useful answer that will work for the question at hand, whether it's building a power dam or explaining the transformations of Mercury? I'm not going to be here to be a psychologist here to figure out who we are. I just want to say that I put in Kawase here. This was an effort, 20 years ago, to try to get hydrology recognized as real science in the sense of getting the kind of money that ocean sciences and atmospheric sciences get to show that we're scientists instead of just people that go around and solve your problems for you. But I don't know. I'm not here to be a psychologist. I'm here to be a preacher. Because in our efforts to get hydrological answers for complicated issues, there is a cardinal sin that many of us, some of you out here probably, are guilty of. We want to help solve geochemical questions. So we should tell the biogeochemist where their water has been. Unfortunately, there's a great temptation to take geochemical information about chloride, sodium, organic carbon, and try to think that that is some sort of a tracer of water. So instead of telling the geochemists about where the water is so they can solve interesting chemical problems, we take their information. Here are two of the latest examples. I examined a thesis just 2 months ago. Really impressive stuff. This is a diagram from these Plinlimon, where they have 7-hour chemistry across the periodic table for like 18 months. You get this wonderful input signal in the rain that's very noisy. You see a signal that comes out in the stream. And by applying amazing Fourier analysis, they will tell you how long the water has been in that catchment and where the water was going. And I'm like, well, geez, that's really amazing to tell us hydrology from this output signal of geochemistry. But it means we have to assume that these chemical quantities are working as conservative tracers, which they're not doing. If we could know the hydrology independently, we could say so much more about the chemistry. This person, Joachim Rimmel, went on then to look at hypereic storage. Nice big equations, working out amazing stuff. He put in different pharmaceuticals as tracers again, and told us things about the hypereic storage. but again had to assume that some of his tracers were real conservative tracers, and they're probably not. Personally, I'm very concerned about all we know about the hyperrheic zone, how much of it is just imperfect tracer behavior, put in bromine or rhodamine. Very glad you'll have next week somebody who uses other tracers that are hopefully less susceptible to this being misleading. So this is one thing I'm very concerned about in hydrology, is that we do some, here's the worst sinner of all, n-member mixing analysis. I'm sorry, Rick Hooper, about this. But here we have somebody creating this sort of source space of oxygen 18 is one tracer, dissolved organic carbon is another tracer, and they have their pore water, they have their throughfall, they have their groundwater, and these are their source areas, and the stream is made up of these. And it's like, please, organic carbon is not conservative. It transforms at different time scales. This is the kind of thing that I've left the name off here so you don't have to see who's behind this, but I feel that if we could do a better job of the hydrology, we could take the information in that organic carbon and do so much more. So this is partly an advertisement for the campaign for real tracers. Don't use geochemical information as tracers. Use the oxygen 18 or the deuterium, something that really is a tritium, a tracer of water, borrowed from the campaign for real ale, by the way. What are some of the things we could do if we understood the hydrology well? Well, in Sweden, we are busily trying to replace fossil fuels by harvesting more forest and burning it as biofuels. And I went to Sweden to study acidification. Actually, with Howard, you got me started in the acid rain business. They're very concerned about English pollution acidifying Swedish soils. Well, now the amount of biofuels we are taking off on an equivalent basis are greater than acid rain ever was. And nobody in Sweden is really concerned because we're doing it for a good cause of creating biofuels. But I would really like to know what the weathering capacity is to neutralize or to generate calcium magnesium that could replace what is coming off in the harvest of biofuels. And for this, we need to know weathering, and we need to know the flow pathways and residence times of water really explicitly. I'll come back to that a little bit later. This is one challenge I would like to get at with hydrology. The other challenge, I didn't think I would bring this, but a few months ago, I was listening to Yihun Deal defend his PhD thesis on the future of water in Ethiopia and the role of rainfall harvesting, done at the Stockholm Resilience Center. This is cutting edge stuff. And halfway through the PhD defense, they're talking about, is there overland flow or not in these Ethiopian highlands? And can we rely on the SWOT model's representation of flow pathways? I can't believe this. I thought I was going to hear a really transdisciplinary discussion of sustainability, and we're talking about flow pathways and water again. So we need the hydrology if we want to understand not only geochemical issues, but even broader issues for how the food and water security in a place like Ethiopia. So we need some good hydrology. I hope I made a case for that. And now I'd like to introduce you to the sandbox, Sweden, where I was sent I went many years ago, of my own volition to try to get some hydrological answers. And this is a picture of old Uppsala, where there's some burial mounds that were 1,000 years ago put up. And this is an old picture. It's about a century ago, because a century ago, the distinguished professors of Uppsala University, which I'm now a member, were convinced that Uppsala was the center of culture in Europe. They were even thinking that Atlantis might be somewhere in the Swedish landscape. So these guys thought that the answers for Europe, the origin civilization, were there in Sweden. And essentially, I'm telling you the same thing. If you want to understand hydrology, if you're tired of working your complicated karst systems or this Canadian shield or whatever, come to Sweden, because we have a simple landscape there. And it's simple because of what the glaciers did. Instead of giving us a nice, even layer of till, let's say, that gets more and more compact as you go to the bottom, so no nasty bottom situation. And we got a reasonable amount of slope, nothing extreme, a reasonable amount of slopes, so no erosion. We have a water table you can access with a shovel or some sort of tube you can put down in many places. And we have some very good textbooks. This came out 30 years ago. It's called Water's Way from Rain to the Stream. Some lovely, simple pictures like this, and if you can understand them, you should get your PhD in hydrology, because even though it's simple hydrology, it is still plenty of complexity. And not only did they have simple hydrology, they were a place that was pioneering the use of oxygen-18 and deuterium as tracers, seeing that this big variation in the rainfall was highly damped as it came out into the stream. So some of the early papers saying that, hey, wait a second, what comes out into the stream is not the rainfall, it is old water, came from the Swedish landscape. And they sort of set us up for some of the work that Jim Kirchner challenged the hydrological community with, saying how badly we were doing with this double paradox. We said that we get old water. We go from little flow to a lot of flow very quickly, and it's the same water. It's not the rainfall. And to make it even worse, the chemistry that comes out with that old water, the water chemistry sometimes changes dramatically. Some things go up in concentration, like my beloved organic carbon. Other things go down in concentration, and some things don't actually change much at all. How does the same old water give us those different responses? Well, I've been looking at this kind of chemistry for years in Sweden. Chloride staying stable, carbon going up as flow goes up. This is spring flood, and the calcium going down. And to me, that wasn't a problem at all. What's so difficult about that, Jim? So, because we'd been looking at the stream and what was near the stream, and we could say that the answer to this double paradox is a piece of cake, or I would like to say a riparian layer cake. If we go into the soils near the stream in our nice Swedish boreal tills, as the stream level rises, as flow goes up, the water table rises. And as the water table rises, it rises into different layers, and those layers can have different chemistries. Some chemistries, like organic carbon, increase with concentration up the layer. Other chemical substances decrease as you go up the layer. If this were calcium, you'd have less and less calcium towards the surface. And other things like chloride are equal all the way across the horizon. So by just changing the layer that the water comes from with different flow conditions, we get the variable chemistry. Very pleased to write that up in a paper and sort of say that hydrology, it can work. If we understand the hydrology correctly, we can solve these complicated paradoxes. But you've got to have a system where you can understand the hydrology. And thank goodness I was sent to a system that is simple enough. The way this occurred to me, by the way, when I was doing my PhD, was we had an acid stream here, and we had a complicated model of the Birkenes model of geochemistry of weathering, and we wanted to figure out, I could see that how long the water spent in the catchment would depend how much weathering was generated and that would neutralize the acidity. So I dug into this catchment, innocently thinking that if I have a model with boxes, I should go and find the boxes in the landscape. I now know much better. I'm sorry about that. But when we dug into this groundwater, it wasn't acid at all. It was pH 7, 7.5. And it had become acid in the course of a few days traveling through this mysterious riparian zone, which I then had to learn a lot more about. It seemed very complicated at the time. How do we get so much acidity out of the landscape? Now looking back on it, it was a piece of cake. Why was it so hard to understand? But hydrology had to come first, and then looking at the chemistry. So what I feel we've learned in the Swedish experience, if we want to understand our water chemistry, we have to get down into the stream and look up at the hillslope. Don't go up to the top of the hillslope and look down at the stream. Go to the stream and look up and see what is around you. And what you see is a riparian zone here that has been shaped by the flow of water over centuries. And that where the water congregates, we have less oxygen. Less oxygen leads to the organic matter that is fixed by the trees, breaking down more slowly. We develop organic-rich soils. Where we do not have concentrations of flow, areas like this, we have more oxygen, less organic carbon building up. And that difference in organic carbon influences the flow pathways, the topography influences the flow pathways, and they give us the chemistry of our water. So at a long-term scale, the topography shapes the flows, which shapes the soils, and then a short term, adding rainfall or taking it down will change the flow pathways and change the carbon coming out of it. After about 15 years or so, my colleague and friend Jan Seibert said, Jan, can you sort of take this simple picture we were working with and formalize it mathematically? And so we we wrote this nice paper showing about how if we can predict the flow of water, this is the amount of runoff given a certain water table level, we could observe this relationship of flow and water table, would tell us where the water is flowing. As the water table rises, most of the water is flowing right under the water table, under the groundwater table. And then we would see profiles of chemistry. And just mix the chemistry with the water, takes the chemistry of the layer, goes to the stream, and we could explain the double paradox. And it's a model we have tried to use for a number of systems. And you might say it's sort of like Alice through the looking glass, saying that the world is sort of like chess. It follows rules, not exactly. And that's where some of the great interest is why doesn't our model of riparian control or anything else work the way we think it should? But it's to give us a way to see the landscape that is ordered. And if we take this example of organic carbon in our RIM model, this, by the way, RIM-LIT is a word for, the model is called the Riparian Integration Model, RIM. RIM-LIT in Swedish means reasonable. So we have reasonable simulations of the organic carbon. This is looking at 10 years of organic carbon chemistry. And here's a stream. The red are observations. And that stream is driven by temperature. Flow doesn't change the chemistry of the organic chemistry, but as it gets warmer in the soils or colder in the soils, it goes up and down. We can explain over half of the variability over 10 years using this very simple RIM approach. We have another stream. It's a very different response. It also goes up and down a lot, but it goes up in response to flow. This is a flow-driven system. And again, the RIM model can capture this by seeing how the chemistry varies with depth and how the flow varies with depth. It seems to work well. And with just a simple model, we can not only reproduce what we've simulated, but we can see that since the flow and the temperature that are the major controls of the water chemistry in carbon or mercury or lead, we have this sort of, if we look at the flow condition and the temperature condition, we can predict what the chemistry will be. And then we can look at how often do we have a certain combination of flow and temperature. And during summer, this is the most common situation. In winter, this is the most common situation. This is a system that changes primarily with the flow, and temperature is not very sensitive. We can say things about the future and solve it analytically through repeated application of the chain rule. Do not ask me to explain that. This is what the brilliant graduate students do. But we think we've got a tool to look into different conditions of flow and temperature, which some people would call climate change. But since we know so little about what will actually happen in the climate, I'd rather just see it as to be able to understand how certain drivers are going to drive the chemistry. And it all started from understanding the flows well, what I would want to say. Now, what have we been able to do with this other than say something of this organic carbon, which may or may not be of interest to you? Well, acid rain was was what I went to Sweden to work on. Started with the long-term, wanted to know the weathering and the effect of sulfur, discovered that organic carbon was in fact driving much of the pH declines and making the streams acid. And when we understood there was a natural component of acidity, and Sweden was busy because they didn't want to wait for England and Germany and Poland to reduce the air pollution. Sweden wanted to go out and use helicopters and spread limestone in the landscape to save the fish. And one of the things they're most concerned about with saving was when the snow melts, the pH would drop like a stone. And they had to stop this acid shock every year. And I was learning about organic carbon and seeing that organic carbon, organic acidity actually went up during spring flood. And before you lime this, let's try to understand if it is naturally acid or acidified by air pollution. And knowing what we did about organic carbon and the flows, we were able to go to streams from the coast up to the mountains. And over in 2007, this was Hjalmar Loudon's PhD thesis, each of these bars is a stream going from its high pH at base flow to the lowest pH during spring flood. And you can see that pH 6 is what was deemed to be natural. Anything under pH 6 in Swedish policy was acidified and was fair game to bring in the helicopters and hit it with limestone from the air. And the idea was that all these pH decline, all the pH went under 6, that was acidification. But understanding organic carbon, where it came from, in its influence on water chemistry, we could show that the red here is what the sulfur was affecting in the pH. And the blue is this natural shock to the pH that we got from the organic carbon. That was a real eye-opener. If we look at this, there is a huge natural pH decline that we wouldn't have understood without first understanding organic carbon and where it came from. And by being able to predict that, we could then look at what is not explained by our organic carbon model. What does the sulfur explain? And that was this extra human influence. It didn't stop the liming policy from spreading what is about 100 million crowns of limestone for the last 20 years to hold back these spring flood pH declines. But if you look at Swedish policy, their environmental goal is only natural acidity. So I can say we had some influence. They've defined their goal as respecting natural acidity, but they are not, unfortunately, using these models to actually find that organic acidity. Now, the next breakthrough I'd like to talk about that comes from understanding the hydrology is an early spin-off. It's mercury. I hope none of you had fish from mercury at lunch, because if you were thinking of mercury is a really nasty pollutant. This is a diagram of mercury in the hair of women. The yellow line is the hair of women who eat fish regularly, and the blue is women who do not eat fish regularly. This is some work from near Montreal. And you can see that the women who eat fish, they have more mercury in their hair. But this is 9 months during pregnancy. You see, in both cases, the amount of mercury in the woman's hair went down during pregnancy. Where did that mercury go? It went into the fetus, which is the most sensitive life stage we have for the neurotoxic effects of mercury. So this is why we don't like to have mercury in our fish. And unfortunately, in Sweden, every single lake that has fish of any size, it is a restriction on the eating of it, because there's too much, the best we know about what is toxic. So mercury is something we've been struggling to understand where it comes from. And it's not just the total mercury that's the problem, it's this thing called methylmercury, which is maybe 1% of the mercury in the environment. And in 1990, they've been measuring methylmercury in the rain, 0.1 nanograms. They had methylmercury in a stream, half a nanogram, 5 times more. The catchment was doing it. And they made the first measurements of the amount of methylmercury coming out of the throughfall underneath the tree crowns. And they went out and immediately published a paper saying the source of methylmercury in our streams and our fish is throughfall, because they felt that throughfall is what is feeding the stream. This idea of Hortonian overland flow. It's so easy and simple. And when I saw this, I went, wait a second. Don't they understand that if we follow a raindrop off a tree, it does not go over the ground surface. That raindrop goes down to the water table and then begins moving in the saturated zone towards the stream. Really basic stuff. Hydrology 101. But it is not in, many people, unfortunately, don't understand this. So you can say something crazy like the methylmercury in the throughfall is the methylmercury in the stream because it was roughly the same concentration. Here we can see my favorite diagram of, again, organic carbon, not the methylmercury, but organic carbon. And you see that when the water comes in as rainfall, it goes into the moor layer, the upper few centimeters of very organic rich soil. And it'll have 10, 20, 50 milligrams of organic carbon. And then it goes deeper into the groundwater, and that organic carbon is gone. You want to clean drinking water. The best way to do it is filter through sand. The Swedish catchments are basically big sand filters, and they have very low organic carbon. And that water moves towards the stream, and at low flows, the water table is at maybe half a meter, 2 meters, very clean, low organic carbon concentrations. But then, just before getting to the stream, if we've got a bit of a riparian fen due to pollutification over thousands of years, you'll get some organic carbon. Not 1 milligram of organic carbon, 7 or 8 milligrams of organic carbon, and a little bit more methylmercury than you have in the groundwater. But when the water table rises, we may go up by 20, 30 centimeters, most of the water is flowing here, and it's intersecting higher and higher concentrations of carbon, of lead, of methylmercury, giving us the increases we see in the stream. It's a very different picture, but it comes from knowing the hydrology. So again, if we take a water molecules perspective and we follow our flow through the catchment. We start as rain, nothing in the way of carbon, lead, mercury. Hit that more layer, woo, we're bathing in all these nasty things that are dissolved in organic carbon. But we go down to the Podzol layer, and we're suddenly low in organic carbon, low in those pollutants, and we hit the riparian zone in the stream, and we're high in it. This is the pathway of water. There are very few bypasses in the forested teal landscape. Wetlands are another story entirely. I don't want to say anything about those. But for the 70% of the landscape that is till, with just a bit of organic matter at the bottom, this is the dominant flow pathway. Now, we've used this rim modeling approach and looking at organic carbon, going through the periodic table. Lead, aluminum, nitrogen, lanthanides, actinides, strontium. It seems to work reasonably well. And we come to the organic carbon, the carbon that I wanted to talk about. By looking into the groundwater, near the stream, we could see these 10-fold above atmospheric concentration of CO2 in the groundwater. And you would see some of it in the stream, but not much of it, because it's evading so quickly. Now, we did a lot of work to look at the evasion of carbon from the stream, and we could confirm the picture we could predict already from understanding the groundwater and the hydrology, that we were going to be getting a lot of terrestrial carbon coming into the stream, and it was going missing because it evaded so fast. So we did the evasion work, and we've got this picture now of doubling the amount of carbon coming out of the boreal landscape in the aquatic conduit, which we're then trying to think, how do you get so much carbon? We're using carbon-14 to try to see if it's young or old and where in the catchment it comes from. Is drainage to increase the loss of this carbon or change the age? Fascinating stuff, but it started with some basic understanding of the hydrology. Lovely stuff. Using this understanding of how the flow and the riparian zone affect the carbon in surface waters, we can go from our little streams and look at, here are 200 water courses that have 20 years of data. And we can take this simple picture of the flow and the seasonality is represented by temperature, and we can explain between 25 and 75% of the daily variation in organic carbon over 20 years. It's pretty impressive. We can say how much the discharge is influencing the water chemistry, the organic carbon, how much the temperature is influencing it, and then we have sort of a trend. Now, what good is the prediction like this for? We'd love to go into the future. Very difficult, because the biogeochemistry of carbon may change as climate changes, as the vegetation changes. But if we have this simple predictive model that works pretty well in the past, and we use it to the future, it becomes a sentinel of change. If in 10 years' time the system is not behaving like it did for the last 20 years, we can see that something is happening. So that is how I justify trying to use the RIM model to see into the future. Using this kind of understanding. When we apply the RIM model to the last 20 years, we'll find some systems like this, that the chemistry changes mostly with the flow. Another system here, flow has very little influence on the DOC concentration, but the temperature of the soils, that is the big driver. We see these types of extreme responses and mixtures between them in our 200 water courses. To our frustration, we cannot find any landscape parameters, the wetland area, the slope. None of these seem to be able to predict whether it will be a temperature-driven or a flow-driven system. But we're working on that. Maybe we'll get there. But we've come a long ways, I think. Now, what I've said is a sort of a simple story of, gosh, you look at a Hillslope and you can predict so much. But you should be very careful about anybody that says they have an answer. We all know that. You should, oh my gosh, my time is really rushing on here. We're not happy using one Hillslope. If we think a Hillslope explains things so well, we should go into a landscape, in this case 70 square kilometers, and we should look at many Hillslopes and see if they are all giving a similar story. And so we've done that. We set up what we call a Riparian Observatory, sent out a graduate student, Thomas Grabs, put up a dozen of these riparian observation systems to see what comes into the stream. Because the chemistry of the boreal zone, it may look very boring, that picture I had of the boreal zone, but if you look at the organic carbon chemistry, my lovely example again, we have anything from 2 milligrams of organic carbon to 60 milligrams of organic carbon within a few square kilometers of each other. As we go to larger scales, that variation varies, But if the hill slope is such a wonderful explanator of what comes out into the stream, we must have hill slopes with different configurations that give us this great variability in chemistry. And we've gone out, we've measured lots of soil profiles, and we've got a picture that our landscape is made up of a mosaic of wetlands, lakes, and our forested hill slopes. And together, they can give us this riparian model. They can give us a variation in organic carbon that is, the magnitude of variation is the same as the variation we see within that landscape, that order of magnitude variation in carbon over time. What is a bit frustrating is we predict our carbon, and what we observe, we actually have a bias. And I'm afraid, I don't want to go into it now, but Horton overland flow that I like to avoid is actually there. We have systems that the water comes very near the surface. And that water near the surface, it's hard for us to characterize the surface water chemistry and to know how it works. So I'm afraid I can't avoid Horton forever. Something that I think the rest of you who want to work in landscapes should not be running away from is we've also been looking at the specific discharge. We went out and made some salt dilution observations with hydrology. I thought it was so simple. We looked at the specific discharge in this kind of a landscape on a day with sort of medium average flows, and we get from 0.5 millimeters to almost 2 millimeters per day in that same landscape. Like, wow, is that for real? Is this just a sort of, we look at one day and it'll vary out over time? We've now looked for 5 years at 15 sites. This is one hydrograph. And we look at the specific discharge at our 15 sites represented by the color on this diagram. If you go at any one time point, you'll see that there is actually quite a variability over the course of 1 week in the stream. And over the course of a month, there's a variability. And over the course of 5 years, we still have plus minus 20% coming out of different small catchments in this landscape. It is really frightening. So yes, there is simplicity in some aspects of the flow pathways, how they change with the antecedent moisture conditions, but there are also variations in what this landscape delivers that we're going to have to wrestle with. But to get towards the conclusion, I just want to say that the riparian controls, it's the last thing the water sees before you get to the stream. They are a place to begin if you want to understand what's controlling your water chemistry. They won't explain everything, but they might explain a whole lot before you go looking for more complicated answers. They're simple, they seem to scale to the landscape, and they're flexible. You know, we get different kinds of riparian configurations and different catchments, and they seem to match up with what we see in the water chemistry. So what are we going to be doing? Well, I went to Sweden 25 years ago to work out flow pathways and do the geochemistry, and now we're finally going back to do it with the help of Keith Beven and his MIPs model. So we'll understand if Swedish forestry is sustainable by taking the hydrology and giving it to sophisticated geochemical models and say, what is the weathering? Because we have great uncertainties in the weathering of the landscape. I'm sorry, it's a 5-year program we're running on this, and our secret weapon is going to be this kind of representation of the hill slope that we'll then use with geochemical models. If anybody else can tell me where the water is going, I'll give you those data. 10 years of water level isotope measurements will try to model that hill slope. Working in Ethiopia again to try to understand the flow pathways there. The Mercury work has led very nicely to a cooperation with the State Key Laboratory of Environmental Geochemistry, so we've got lots of chance to compare our Swedish landscape with Chinese rice paddies and understand methylation in those zones. So if you get your hydrology right, you can go do lots of things in interesting places around the world. My discipline is called, I'm professor of aquatic climatology to understand how climate influences the water and how the water influences the climate. So these are the things I'm trying to do in that. I can't do it alone, so a big part, it's been really nice to come to this institute to see how you try to get people together. Because what I feel much of my time now in Uppsala is to try to take all the different research groups with an interest in water, hydrology, geochemistry, biology, and get them to cooperate through what we call the Uppsala Water Center to work better at understanding the mysteries, which even if we have, I think the hydrology is simpler there, but we've got plenty of mysteries to work with. Conclusions, you don't need an axe to go and reveal nature's mysteries. You need a good hypothesis. I'm just amazed with took at this spring flood or the methylmercury, that this is really complicated. You look at it for a few years with a good graduate student and an understanding of hydrology, and things make more sense than I ever would have hoped to believe. And there are many very complicated models out there, but I think simple identifiable models such as the rim model I've shown here are a great place to begin. A sort of a counterpart to the models with all the bells and whistles and processes that we can never calibrate reliably. Start simple and then see what we have to explain afterwards. And we need many people who understand the basics of the hydrology, because if they don't understand the hydrology, they'll do these crazy things they did with the methylmercury, that it goes right from the trees into the stream. We need people who think in terms of flow pathways and residence times. They may not have to solve all the problems. They got to think about how does water get there. And I am so glad to see whatever students take the time to study water. And in Ethiopia, they really believe in education as the way to the future. They're pumping out graduate students and master's students. If you want to supervise somebody in Ethiopia, contact me. There are students who need good supervision. If you want to have a simple system to work in, talk to me about the Swedish sandbox. It is so simple. You don't have to go find more complicated systems. And the last, imploring to you, if you want to do hydrology, to help geochemical modelers, don't take their geochemical data and use it as some sort of a tracer. Do the tracing of the hydrology with real hydrological tracers, and then provide your geochemical colleagues with a good description and let them do what they should do best. Thank you very much. Now maybe it's time for the real ale, and this is one of my favorite Calvin and Hobbes cartoons. Look, a trickle of water running through the dirt. My afternoon just got book solid. In my case, my life got book solid when I found that trickle. Yeah.
All right, time for questions, and I think someone's running around with a microphone. Howard.
Thanks very much, Kevin. It's a great talk, and lots of really interesting science and societal issues. A simple question. I've been learning about the cold for the last 4 years, and you didn't talk about it.
The cold, right.
So I believe that you have snow in Sweden.
Lots of it.
And maybe some frozen soils, and maybe some runoff processes associated with that.
Yeah. That was when we started the work on the spring flood. That was one of our side projects, actually. This transect that I've been doing so much with started to look at, is the soil frozen during spring flood, so that the neutralizing processes, if the sulfuric acid gets into the soil, will be short-circuited. The hydropower industry said, we don't need to have soil frost in our models because they work just fine without soil frost. The geochemists, they said, we've got to think about this soil frost. So we did a lot of work, and we discovered that where you have snow, it's a wonderful insulator, and you won't get more than a few centimeters of soil frost. So soil frost does not seem to be a big player in this part of the boreal zone where we get snow that comes generally before the soils have gotten very cold. In the 20 years I've been working, we've had 2 years with very deep soil frost, maybe half a meter, but we haven't had snow. There's not been much runoff to divert over that surface. So it's been less of a player than we would have expected. But on the other hand, in those 20 years, we had 1 year where most of the streams froze to the bottom. What that does to life is, whether it's every 20 years or every 50 years or every 5 years, that is another big player. So I don't want to downplay the role of frost. It is big. But in terms of influencing flow pathways in our forested slopes, I would say it's not a factor. I have colleagues who disagree. We still do research on this, but I don't think it's been playing a role here.
Jay, did you have a question?
Yeah, I really liked your figure with flow, temperature, and DOC, and I was wondering where those temperature values came from the soil or from the stream?
Thank you very much. It is the soil temperature. I downplay that. If we have a model, if this riparian model is just driven by flow, and we have the riparian zone as a chemostat, whatever comes in the riparian zone, it leaves with the chemistry of that chemostat, but not one chemostat, but a layered array of chemostats. we found that that'll explain some streams pretty well, and it won't explain some streams at all. But if we let some sort of seasonality come in, which we can represent by a running average of soil temperature, so that chemostat shifts a bit over the year, we explain so much more variability in our landscape. Now, temperature is what we like to call it, but it's not temperature. That's a proxy for the biological processes going on. But it is soil temperature. And when I went to that picture of Sweden predicting those 200 larger watercourses, it was soil temperature plus a lag time between the soil temperature and when you sample. Very nice. We've worked out the residence time of in 100,000 lakes. And so any point in the landscape, we can say, how long did that water spend in the surface water system? And there's a relationship between our optimized lag time between soil temperature and predicting the seasonality in organic carbon. That relates to this calculated residence time of water. So it thinks the soil has an influence on the water chemistry as long as the water's in the soil. But as soon as it gets into the surface water system, the soil temperature doesn't matter. It's really reassuring that lag time corresponds more or less to our calculated theoretical residence time. I'd like to do more with that residence time work, by the way. So,
okay. Quick question from students in the class. Yeah, at the back here. Got to run, Ali. Got to run. Okay.
DOC?
Well, probably. One thing that's very clear, I was going to get a big research project to look at this temperature effect, and I went to the literature, and somebody had actually taken peat samples and leached water through it at different temperatures. It had no effect on the concentrations. But they took those samples in June, July, August, and September. The season they took the samples had an impact, but not the actual temperature. So, yes, the temperature is just a proxy for all sorts of other interesting processes. This is where you've got to go beyond the simple model, but at least you've got a starting point to look at.
Okay.
Colin.
Switch maybe away from water a little bit. I just was going to, thanks, Hallie, ask a question about the weathering and the biologic acidification, which you didn't talk about in detail, but I'm curious about, you mentioned it's worse the biologic acidification or harvesting, removal of nutrients is worse than the acidification from anthropogenic deposition. I'm just wondering, I assume you've seen changes in the soil pool for nutrients-based cations, and whether there's work that shows potentially direct access of nutrients from the minerals by the plants themselves, if that's something that's being considered as a mechanism to supply the needs of those forests. The weathering uncertainties on this Farpaget catchment I've been working on. There are 8 published estimates of weathering. They vary by over an order of magnitude. The difference between having whole tree harvesting and not harvesting at all is a factor of 3 in terms of the amount of base cations we pull out. So a paper came out a few years ago saying forestry doesn't have to worry about acidification because we don't know the acidification within a country mile of what matters for management, which is a real slap in the face to the huge investment Europe has made to reduce air pollution to get to these critical loads estimated by a weathering model. But then the forest industry says, oh, that weathering model isn't really so good, so why bother? I mean, okay, why don't we turn on the sulfur in the smokestacks? So the question is, how well can we really know weathering? That's what we're working on. A big question is biological weathering. Can the trees get at things? We have people working on that. I discovered at my university that when I was coordinating the acidification research, more papers about weathering were coming out of the mycology department than everybody else. But they weren't talking about quantifying weathering. They were talking about these genes go on that species disappears. They couldn't quantify it, but they are definitely seeing that the trees affect their environment. I would say at the end, after a couple of years of research, we don't think it is it is going to help for calcium magnesium, because trees don't need calcium magnesium. They can do with so little calcium magnesium. It's the streams and the fish that need the calcium and the magnesium. So I would say, it's the biological weathering. We're doing it, but I think it's much more interesting is what is the flow, this residence time of water? What can a catchment deliver to a stream? And there, if we take a model that is one mixed box, that will give one answer. But if we have a box that is very slow and very high weathering products, and a box that is very fast and low weathering products, where you have low weathering products and fast flow, that's where the weathering goes fastest, because when you build up a reaction or product, you slow down the reaction. It's very counterintuitive. Deep soils, geez, there must be a lot of weathering there because there's a lot of calcium in the groundwater. That's probably where the weathering is going slowest. We don't know. That's what we're trying to, if we can get the hydrology right, please help us get the hydrology right, then we can talk to the geochemists. So that's what we're hoping to do in the next few years. And that's why Ollie was here to say, I can model these flows. Great, please come do that.
On that last point, so you showed very nice variance collapse of DOC with catchment area. And then you showed a very nice variance collapse of specific discharge with catchment area. Are they the same? And if so, why? And if not, why?
Right. No, they're very, very different, because the chemistry, the DOC is not related to the flow, but it has the variance collapse is just the way when you have a network and you add it together. So that's the simple statistics of it, but it's not because the variance of DOC and the variance of flow, specific discharge, were related there. What has been surprising is that variance collapse, in space it collapses. And in time, as we go to longer aggregation periods, it gets less, but it does not go away. And I think this is going to force all the work we've done with export of elements from that landscape are going to have to be revisited, because we used one weir to get the flows all over the place. So I'm just...
This is getting at your kind of representative elementary area for the landscape, perhaps.
Yes, and it's a relative elementary specific discharge. That, I think, has been a gross oversimplification in this particular landscape.
Yeah.
I'm very curious if other people have that problem.
Okay, well, it's just on 5 o'clock. I think we'll adjourn to Alexander's. Hopefully everyone can join us. And thank Kevin for a really interesting overview of Swedish hydrology, issues of flow paths, and the Mercury situation in Scandinavia. So thanks very much, Kevin.
Thank you very much. Gotta go.